Let's start. All right, so today is tutorial 8, and we'll talk about deep reinforcement learning. Okay, you should have watched, this was the lecture before the geometric learning, so you should have watched the lecture about this. Specifically, we'll cover the setting of reinforcement learning and the differences between the other settings like supervised and unsupervised. We'll show a framework for doing reinforcement learning called OpenGym, and we'll use it. And we'll learn to play Atari games, basically. We'll implement an algorithm called deep Q learning and solve games for the ancient Atari platform. Okay, so let's start. First thing, we have to kind of remind ourselves about the setting of reinforcement learning. So again, this was covered in the lectures. I'll just show the main parts that we're going to need for our implementation today. And I'll try to go over it briefly. So in reinforcement learning, we have a general learning setting where you have some agent acting on some environment by doing some actions, and the environment is something that has some partially observed state, and you get some observations from the environment and a reward based on what actions you're performing. So basically, you have an agent, you do actions on the environment. You can't see the whole state of the environment, only some observations are available to you, and you get a reward based on what you're doing. So that's the general kind of concept of reinforcement learning. So in the example of playing video games, the agent would be the actual player that decides what to do. The actions are the kind of movement of the controls or the buttons. The environment is the internal state of the game. Maybe even other players, so you can't influence it, and you can't maybe see everything. You don't know what's going on in the other players' minds, but you have observations. For example, what you see on the screen, that's your observations. Okay, and you get a reward, let's say a score. So far we've seen supervised learning, where we learned to map samples to labels, basically. We've seen unsupervised learning, where we learn some kind of latent structure, maybe a manifold where the data actually is, instead of an entire space. We learn some structure. But in reinforcement, it's not exactly the same. It doesn't cleanly map to these, because on one hand, we don't have any predefined labels, but we do have a reward system that kind of tells us what actions are good and what actions are bad in some way. So we want to observe these rewards and expect our agent to learn how he should behave to increase the total reward. So we kind of create our own labels while we are experiencing, while we're running the game and experiencing different things in the game and getting rewards. Okay, so there are some unique challenges in reinforcement learning. First of all, the observations are not, you can't think of them as being sampled IID from some space, because they depend on the agent. You have some kind of trajectory based on the actions that you perform, and the next observation that you see will heavily depend on what you saw before and what you did so far. Okay, so that's kind of the one problem, and another problem is that it's hard to discover new strategies, because if you kind of use your agent, you're not finding out different things that you might. You could have sampled from a different part of the space, let's say. And another issue is that the reward signal is not necessarily, doesn't exactly come together with the action. Sometimes the reward can be delayed. Maybe you play a game of chess and only after the final move you know if you won. Okay, so you might have a delayed reward. There's no score in the middle, maybe. Okay, so it might be the case. So these are unique challenges. Now, to better define kind of the domain and the things that we'll need for our implementation, let's talk about Markov processes. So again, as you saw, basically a Markov process is a system where you have states and you have transition properties from state to state, where the probability to transition is only dependent on the current state. Doesn't matter how you got here. When you're in a specific state, you have this probability to transition from state I to state J. So it's a distribution over the states, conditioned on what state you're currently in. Okay, and sometimes you may reach a terminal state where there's no probability to transition to any other state. If you take a Markov process and add add a reward. You get a reward process. So let's say when you transition from Si to Sj, you get a reward specified by this function. You have a Markov reward process, and we always define some kind of a discount factor, which we apply to future rewards. So we say the discounted reward or gain from time t into the future is the sum of the rewards that I will get, and each step I make into the future, I factor it by gamma, which is usually less than 1. So it means that the farther it is into the future, the less weight I give my reward, my future reward. Okay, and based on that, we can define the value of a state. I mean, it means the expected gain, how good the state is. If it's a state that I expect my reward to be very great when I am in there. Okay. So, by the way, what's the expectation over this expectation? So think about it. What's the expectation over? Yeah, of course it's ZT, but what's the stochastic part? When you do an expectation, you have some sum and some quantity times the probability, and you have to sum something. So the expectation here is over the transition probabilities of the states. You start from a specific state at time t, and then you have a distribution based on that state, distribution over all the other possible states. Okay, and then the next step, the same thing, and you keep going, so the expectation is over the states. Now, what we will work with is a Markov decision process where we also have a set of actions that we can do. So let's say we have this action space A, and now our transition probabilities, it's still a distribution over the possible states, but now you have to condition over the current state and the current action. So when you perform an action in a state, you have a distribution of possible. Your next state is stochastic, so you might end up in various states based on the action that you performed and the current state that you're in. All right, and we have defined the immediate reward like so. We say it depends on the current state and the action you performed now. Okay, we drop the next state. So if you're at a state and you do an action, you get a reward. So this is the kind of framework that we need. And now we define one more thing, the policy of the agent. So this is a conditional distribution. So now you have a distribution over all possible actions when you're in a current state. So for every state you're in, you have a different distribution of the actions that you want to perform in that state. So all these distributions together, you call them a policy. Okay. And the last thing we need is the action value function. Okay. There's also the regular value function, but again, this is what we need for the implementation today. So the action value function is the expected return when you are in when you start from this state and you perform this action. So it's defined the same. It's the expected return, expected gain, but you condition on the current state, or the initial state, let's call it, and the action that you performed in that state, and you have your policy. So the policy will define the way the actions are selected. Okay. So now again, what's the expectation over? What are the stochastic elements? The stochastic elements are the selection of the action and the transition between states, given that. Okay. So let's write this explicitly. You can see when you look at the sum, you have this part here. This is the reward you get just by performing action A in state S. So this is not deterministic because we have a reward function based on the state and the action. And then you have this part which you have to take the expectation of. If you write it explicitly, okay, so the first deterministic part is this immediate reward that you got in your initial state. But then, so let's look at it graphically. So you were in the state S and you performed action A. Now you have a probability to reach these two states. Okay, so you have to take the expectation over the transition probabilities because that's a stochastic element here. And then to keep going with this, for every state that you reached, you have to select an action. So now you have to insert this policy function to do your expectation. So you have to now take the expectation over the possible actions. Okay, and when you reach when you finally reach the next state, then you have this next value of that state. Okay, so this is the state the action value function Q. So notice that when you have a term like this, as we saw here, if you take the maximal value of the function, of the action value function, you will get a better outcome. Okay, so when it was in the lecture, Alex called it the Bellman operator. If you just kind of take the maximum action, then you will get a better value. So there's this Bellman optimality equation that basically says that if you have the optimal action value function, it has to satisfy this. So it has to be satisfying this equation. So it's similar to the equation that I just showed you, but you don't have the summation over the actions here. You just select the action that will maximize the value. Okay. So this would give you kind of the optimal, or at least the optimal action value would have to satisfy this, based on the Bellman operator that we saw in the lecture. Okay, and furthermore, if you have somehow this Q function, this action value function, you can always define a policy based on that. You just say whatever state you're in, choose the action that will maximize it. Okay, simple. So you know how to build a policy if you have this action value function. Okay, so generally we assume that we're in an MDP environment. Well, not always. There are even more complex environments, but we'll see an MDP environment. But we don't know the transition probabilities, and we don't know the reward function. So basically, what we have to do, we have to learn both the action value function, or sometimes the policy. It's a different method, but we'll see learning action value function, which is kind of how the agent should play the game, what states are valuable, and what actions are valuable in those states. And simultaneously, you have to learn kind of the dynamics, which is the rules of the game, which is these P and R. Okay, so that's the challenge in this setting. And the last thing I need to explain is the concept of experiences and episodes. So these are important terms, very, very simple to understand them. So an experience is this tuple of current state, current action performed, the reward we got, and the next state we transitioned into. So it's just what happened to your agent at time t. And an episode is a sequence of experiences. Okay, and they terminate at some point. You reach a state and the game ends. Okay, so you have episodes are built from experiences of observation, action, reward, observation, action, reward. Okay, and of course the states. It can, let's say you reached game over and then you started again, so it's a new episode. Or it can be until you die, so one life. Let's say every time you lose a life, that's what we'll see in the Atari. Then it will be a new episode. Okay, so now let's look at a nice framework for playing games, at least with algorithms. So there's this nice framework called OpenGym. And they define it as a toolkit for developing and comparing reinforcement learning algorithms. So it kind of does simulations for you, so you only have to focus on the logic of your agent, and it gives you kind of the environment that you can interact with. Okay, it will give you the environment, and you have to build your own agent. So let's see a quick example using Gym. So we'll play, today for this tutorial, we'll play Space Invaders, which is a very classic, nice game. It came out for the original Atari, and I'll just show you kind of starting from the end. I'll show you a piece of code that runs a random agent and plays Atari. So we use Gym. We make an environment called Space Invaders. It's one of the built-in environments. There's lots of environments, not just for Atari games, for many other things like physics simulations and stuff like that. So we make our environment, we wrap it in a monitor, you'll see it later, just so we can record video from the game. Okay, and basically what we're doing here is until the game ends, we're taking an action. So we have some action space, we sample from that, we get some action, we'll see later what the action is, just a number in this case. We'll give the environment the action, we say do the action on the environment, and then we get an observation. Okay, so we did that for 583 steps, and we got a total reward of 105. So let's see what happened. Just have some code here that will show you the video. Okay, so this is the video from the game that I just played. You can see our agent is randomly moving. It's just randomly moving and firing. It's selecting an action at random. So it plays, and then it lost a life, and then it kept going. So this is really what Gym gives you. It gives you some kind of simulator that you can interact with, and it does lots of cool things for you. Okay, so now we'll use that, and we'll try to build the deep Q network. But first, let's kind of see the features of Gym so we can understand what we're doing in our code. So first of all, what is this environment, and how is it built? So usually when you have an environment, you actually have multiple classes of environment that wrap each other and kind of modify the behavior. So we'll see the wrapping. But basically, if you just create an environment like Space Invaders, you can see you have this Space Invaders environment, and it's wrapped by something called Atari env, and it's wrapped by something called time limit. So we'll see later that these wrappers are important. They help you kind of customize or define the environment and the way you interact with it. Okay, so for example, this time limit will cause your game to end after a fixed number of steps. If the game doesn't end, then the time limit will end it. It's an example. So an observation is what you get every time you interact with the environment, either by resetting it or doing a step. So what are you observing? If you look at the shape, it's basically a NumPy array, in this case of 210 by 160 by 3. So this is actually a color image. So every observation, in this case, in this environment specifically, is just the raw pixels that the game is generating. Okay? I can show you by just plotting it with imshow. So this is an observation. This is the first observation in the game. You just got raw pixels. So we will teach our agent to play Atari just by looking at the pixels in the screen. So that's the idea. Yeah. This is the state that you. This is the state, the observation that you see. So we will think about it. This is the current state. It won't be exactly like this because, as you see, we'll have some pre-processing and we'll actually look at multiple frames together as a state. But generally, yes. Because we have to decide what to do. Knowing the reward in the action is not enough. How do I know where the player moved? All I have is the pixels. That tells me everything. So all I know about the environment is these raw pixels. This tells me where my player is, where the targets are. It shows me that they're shooting at me. The reward? In this case, it will not come from it. It won't be from analyzing the pixels of the score. Yeah, the reward itself, the number will come separately from the simulator, but the logic that decides what to do will be completely based on the pixels. Okay, so let's look at something called the observation space. So what are the space of possible observations? You can get it from the environment. So you have something called box. So it just represents a tensor of, in this case, 3 dimensions. It's a 3-dimensional tensor, and it has some range of values. So by looking at that, you can see the range is 0 to 255, which again corresponds to color images. And you can also sample from the space, and you get this is like a random representation of your space of observations. Of course, you won't see random observations. You will see observations from the game, depending on your actions. So what are the actions? You have also a space of actions from your environment. So it's called discrete. Discrete 6 means it's just a space representing the integers 0 to n-1. So we have, in this case, 6 possible actions, okay, 0 to 5. And the meaning of the actions is specific to the environment. So in this case, for our game, the action 0 is a no-op, the action 1 is fire, the action 2 is right, move left, and so on. Right, fire, okay? So move right and fire. That's the meaning of the actions. How do we perform actions? So this loop shows you that all you have to do is call env step with some number representing the action. That's it. When you do that, you get a new observation. Okay, so I just ran it for for 2 seconds in this case. 2 simulated seconds, of course. Okay. No, this is just an example to show you that I did the same action, fire. I just, for 2 consecutive seconds in the game, I just pressed fire all the time, every step. Okay. You can see here, I think this is the fire that I performed. Okay, and we close the environment. So the last thing that we have to see is wrappers that you can use to wrap your environment and modify the behavior. We showed the monitor wrapper. It was something that records the screen and generates a video. So you have different kinds of wrappers that allows you to modify the observations coming into your agent, or maybe modify the reward coming into your agent, or maybe modify your actions that your agent is performing before they get to the environment. So it allows you kind of to customize the setting that Gym is giving you. So let's see an example, because again, we'll need this soon. So let's say I have this malfunctioning screen wrapper. So it takes an observation and it will generate a new observation by inverting the colors, and with some low probability, it will just set one of the color channels to a constant. Okay? Just to show you that I'm modifying the observation on the way to my agent. So maybe this is like I'm doing some kind of data augmentation before it reaches my learning algorithm. So I can sample different kind of images. And here I have this other wrapper that is an action wrapper. It takes an action, and with a high probability, it just replaces it with fire. So this wrapper will cause my agent to just, most of the time, just fire, even though it selected different action. So just for an example, so if I take these 2 wrappers and wrap the Space Invaders environment, and then run this environment after wrapping, okay, then you can see, first of all, it's wrapped by these 2 wrappers that I created, and the original wrappers that were there before, just provided by Gym. Okay, so now our agent played for 800 steps and got a much higher reward, by the way, than the random game. And we can see in the video that the modifying the observations really worked. You can see the malfunctioning screen and the fact that it's constantly just firing and barely moving. Okay, good. So now we know what we need to know about Gym. Yes, because we will use this for the pre-processing for our learning algorithm. We'll use this to process the observations for our algorithm. Yeah. But this example was just not. Yeah, this was just for fun. But it was just to show you how to use the wrappers. Okay? Because afterward, the actual pre-processing wrappers for this algorithm are much, much more complex, and I don't want to show them. I just want to explain what they do. Okay, so now we'll actually solve our problem. So after we know about the setting and we know about OpenAI Gym, we'll now tackle Atari games, and we'll use an algorithm called Q-learning. Okay, so the idea of Q-learning is to use a deep neural network to approximate the action value function Q that we saw before. We have to learn this function somehow, together with learning how to play the game, of course. So we'll again, like I said, we'll teach our model to play directly by observing the pixels that we get from our environment. Okay, so this implementation here is based on this paper from the Google DeepMind team. It was published in Nature, so this is a really serious paper. And they really showed that the same exact algorithm allowed them to play at a superhuman level and completely beat most of the Atari games. Not all of the Atari games, but really the huge majority were played in a really superhuman level by the same exact algorithm. Okay, so this is the same algorithm used for no, that's something else. That's AlphaZero. But it's the same team. It's the same DeepMind. Okay, so we'll learn again. We'll learn a parameterized version of the Q function. Okay, so this theta represents our parameterization. It will be implemented as a convolutional neural network. And we'll treat the task of learning Q as a regression problem, because the action value is just a number. We need to kind of find some function that learns the right number. Okay, we'll treat it as a regression. It's a continuous quantity. And of course, during training, we'll collect these experiences. And we'll denote the ith experience like this. So we have a state, an action, the reward, and the next state we'll denote it by S prime. This, because the action, it's regression because the action value function, remember how it's defined. It's the expected reward that we'll see. So it's just it's a continuous quantity. We need the number.
Give you 1 out of 6 actions.
No, it's not the action. It's the value of the state. So let's say the state is right now the beginning of the game. The screen is full of enemy ships. So you'll get a high state value function because there's lots of rewards to reap. If you now shoot everyone, you'll get lots of rewards. So it's a high. This state has a high value. So you want to learn the value of each state. So for every bunch of pixels, there's a value associated with that you want to learn. And based on that, of course, you need to also learn what action to take. So it's same function. We'll see how it's mapped. So the loss here, because it's a regression problem, we'll build it as like an MSE loss. So this is the action value that we're generating with our deep network, and this is some label. This is our label for the. So this is a pointwise loss. So for the experience I, and experience I, we were in the state SI, and we performed action SI. So our network says we have some action value there, and we need some way to generate this label. That's why we don't have it, of course. So the idea is we will also generate the label, and we'll do it like this. If the next state, S prime, is a terminal state, then it's easy. We just use the reward. So the value of the state and the action now, just before the terminal state, is the immediate reward that we got. Because after the terminal state, we won't have any more rewards. So it makes sense. But if we're not in a terminal state, which happens most of the time, then we'll take the immediate reward plus this term here, which is the maximum value of the action function for the next state that we arrived in, and the best action in that state. Okay? So what does this remind you of, basically, this formula? Bellman, okay. So it makes sense because it's similar to the idea of the Bellman equation, only we dropped this expectation over the state transitions. We dropped it because we don't know it. And the idea is that because we're looking at batches of sampled experiences, transitions that are more likely will be more frequent in our batch sampling. So we'll see them more. So the weighting by P is implicit. So we don't really know P, the transition probabilities, but we'll kind of see it anyway. That's the idea here.
Where does the RI come from?
The what?
The RI.
You get it from the environment. Every action you take, you get the immediate reward. No, the Y's are the labels, the R's are the rewards. You have the rewards. Let's say you pressed fire.
Yes.
So you might get a reward. You might get the reward that your score went up by 2. That's the immediate reward.
How do you know the reward is actually the result of the fire? Because
You don't know.
between the fire and the reward.
You don't know. That's the thing. It's a delay. So you pressed fire now. After a few states, maybe you hit the target, and then you get the reward. So yes, of course, that's one of the problems here. You have to infer kind of what your actions are causing.
But you said that the label YI is generated by us, right? So you need to know how good is the state.
So that's why we use the state action value here. We take the max over it. But there's a nuance here. You use a different parameterization, theta minus, which I'll talk about it in a second. So you need to know how good the next state is. That's the S prime here. But you don't know it because you're trying to learn it. So you will use your same function but with a different parameterization, okay? Which is exactly the point of the next section. So this different parameterization here, this Q of theta minus is called the target network. Okay, so this is one of the important ideas in this paper, how they solved the Q-learning thing. So the problem is that you want to use the action value of the next state, okay, to update the current one. But the problem is if you do that, then generally you'll have a very unstable training, because at least in this kind of games, it's very likely that the next state will be very similar to the current state. It just looks kind of, the pixels are shifted a bit, but there's not kind of large variations. And also, if you kind of immediately change the function that you're using to generate your labels, you're kind of chasing your own tail. Okay, because the next step you'll have a completely different function, or a different function at least. By using a target network, you're kind of keeping the function that you're using to generate the y's, you're keeping it constant while you're learning. Okay, that's the idea. So you're keeping the target network constant for a while, so that you can learn this current parameterization that prevents you from kind of modifying what you're trying to learn and chasing yourself. And okay, so like I said, the target network is a different parameterization of the Q functions. And in practice, as you'll see in the implementation, what we'll do, every some number, like a few thousand steps, we'll take our current parameterization and give it to the target network. So the target network is kind of following the regular action value network. Okay, so we'll move our parameters from the current network to the target network, and they will be fixed until we update it again. Okay, the next idea in this paper, well, this is not a new idea from the paper, but this is something that they're using, is the concept of experience replay. So another issue, like we said, is that the samples that we see, if we just play a game, they completely depend on one another. The fact that I just pressed fire, and before I saw something, and the next thing I see will be the same thing with the firing action performed. So it really depends on the current state, and I don't have IID samples from the whole space. Okay, and this is a kind of problem because we're using stochastic optimization, which kind of implicitly, or not implicitly, assumes that we have this IID sampling. And again, this will the fact that we just use the experiences that we're seeing will create kind of these loops that we only see a small subset, and we're using that also to learn. So we kind of, again, we might get stuck in this suboptimal region in our optimization. So a better way to do it is not to directly optimize on the current experiences that we're sampling. And the way we do that, at least in this idea with an experience replay buffer, is that we keep getting experiences from our environment, and we store them. We put them in a buffer, which just stores these tuples. Let's say it stores the n most recent experiences from different episodes. So you play, and you just put these experiences in the buffers. And when you want to learn or update your model, you sample a batch of experiences. So when you do that, you get different experiences from different episodes at different times. Okay, so it's not so sequential. You don't get, it reduces the probability that you will get stuck in these suboptimal loops where you keep seeing the same thing.
This is actually the data set you're learning from.
Yeah.
Growing
So you're playing, the fact that you're playing generates experiences that you put into the buffer, but the actual learning is not from your playing, it's from this buffer. Okay?
And you do it every few frames.
You'll see in the implementation. Okay, so and the last thing here that they're doing is something they call epsilon greedy policy. So the idea is that initially you start off with some random initialization of your network. So you have a very bad policy and a completely wrong action value function because it's random. And if you just let your agent follow that by just sampling the action that maximizes the action value function, then you may never actually see very useful actions. Okay? Because you don't really have a good policy. If you just try to play with that random policy, you might not sample experiences that actually teach you something. So the idea is that you use this epsilon greedy approach where you let your agent take a random action instead of using the action that maximizes the action value function with some probability. So it's random with probability epsilon, and you use the current policy that you're currently learning with 1 minus epsilon probability. And the idea is, again, you start epsilon high, you start it with 1, and as your training progresses, you believe in your network more, and you start decaying epsilon, so you do less random actions. The fact that you do more random actions in the beginning allows you to kind of play on the exploration trade-off and explore more in the beginning, and then in the final parts exploit more the policy that you learned. Okay, and finally, there's a heavy pre-processing that they're doing. There's lots of details here. It's kind of not immediately enough just to use the theory and implement it as is. So they're doing lots of tricks in the pre-processing to improve the training. And I'm just gonna list them, and we'll see that everything is just implemented by wrappers around your environment. So these are the tricks that they're doing. They start with no ops instead of actual actions, kind of to get to an initial state. They in the case of Atari, some games you have to press fire to start the game, so they did that for the agent, so it doesn't have to actually learn that. And they stop the episode after a life is lost. So in games where you have when you have 3 lives, they just said when you lose a life, the episode ends, because it makes everything kind of it makes the episodes more similar to each other. No, there is a stochastic element in the games. Yeah, it doesn't have to be a deterministic environment. So they're doing some kind of processing on the images, like fusing together frames to reduce the flickering, because if you actually look at the frames that you see, sometimes because of the simulation, some elements disappear, stuff like that. They scale and convert to grayscale. They shrink the images down, convert, and they skip frames. Okay, they only take every 4th frame after this fusing, and they stack together 4 frames. So basically, they're looking at tensors of 4 frames stacked together, but with skips of 4 frames. So it kind of gives them it kind of allows them to see movement, the direction, like what element is moving where. Okay, because if you just look at a single frame, you don't know if the shot is moving towards you or the enemy is coming towards you or things like that. So they're using multiple frames stacked together to allow the agent to use the movement. Okay, so this is kind of a visualization of what frames they're taking. So they're taking each 4th, but they're fusing it with the previous one, and then after they fuse, they stack every 4. So this is kind of the idea of the pre-processing. So luckily, the pre-processing steps are already implemented. You have this OpenAI repo called baselines. So everything is just a few wrappers that you can use. We'll just add one extra custom wrapper that will convert the images from NumPy arrays to PyTorch tensors and change the axis, because in PyTorch we use the channel dimension is always first in images. So that's the only thing that we need to do. So this is our wrapper here. Okay, so it takes it's an observation wrapper, so it takes an observation and it flips the axes here. Just change the order.
So the network is CNN, right?
Soon, you see the network. Okay, so now let's use this Atari wrappers. You can see I put it in the tutorial code. I'm just importing the Atari wrappers, and I'm using this to create an environment, wrap it with this DeepMind wrappers, which is all the tricks that I talked about, and then this is the wrapper that I just implemented above, and then I get this environment, which is what we'll actually use for learning. So we can see our heavily wrapped environment. So it's wrapped by lots of these wrappers, and you can see now the observation space is different. It's smaller, okay, and we have 4 color channels, but it's not color channels, it's actually the frames, yeah. And this is what an observation looks like now. It's grayscale and shrinked, okay, and this is one of the channels or frames in the observation. Okay, so let's look at the DQN model. So the actual model is really simple. The model that estimates this action value function. It's very simple. It's just 3 convolutional network layers. followed by two fully connected layers. And the way they model the Q function is by they take a state and they return a Q value for every possible action. So if you have 6 actions, you will get 6 numbers after your last fully connected layers, and those represent the action value function for each action. Okay, it's very convenient to implement it like this, because then you can select the maximal action by just looking at those numbers and taking the maximal value, the action with the maximal value. So they take a state, so this is the state, okay, an image.
This is the 4 frame.
Yeah, the 4 frames together, they move it, they forward pass it through 3 convolutional layers and 2 fully connected layers. The fully connected layers, after the last one, you get a few numbers. You define how many numbers. So they define that you will get 6 numbers in this case, which corresponds to the number of actions. So the interpretation, the way you will use this is that you will say that's the action value for each action in that state. That's how they model the Q function. Okay, so it's a trivial model. So this is the whole model, and should be really trivial by now for you guys. So you have this convolutional part with three convolutional layers. Okay, and then a fully connected part with 2 linear layers, and the output is the number of actions. Right? Okay. So in the forward pass, you just do the convolution, and then use the fully connected layers. After you flatten all your convolutional features, use the fully connected layers to get the 6 numbers that you need in this case. Okay, so as usual, let's look at the model. It's what we expect, right? And we'll do a forward pass and see, indeed, for the observation that we showed before, the grayscale frames, we get this tensor of 6 numbers. So this is a batch of 1. Okay, makes sense. Yes, basically. This represents the value of each action in that state. Now the experience replay buffer, we need to implement this. So it's also pretty simple. So remember, we need to save tuples of experiences. Okay, so we'll have this maxlen, which says how many we want to save in our buffer. And when we get a new experience of state, action, reward is done, you'll see that we need this. This just says whether the episode is done. And the next state, we just put this in our buffer, and our buffer is a data structure called the DQ, which is like a queue, but it automatically throws out old elements after the length is maxlen. Yeah.
Do you keep states from previous episodes in the buffer?
Yes, it's over the episodes. So the only nuance here is this conversion to CPU. It copied to RAM if you're training on GPUs. You don't want your buffer to store GPU tensors because you'll run out of memory pretty quickly. And that's adding to the buffer. And for sampling from the buffer, we just look at the length of the buffer and get a random choice of indices. So we get batch size random indices, and then we take from the buffer those indices, and we get a tuple. We get a list of tuples. Okay, so this operation here, this flattening of the list into multiple tuples, and then using zip to split it out to the different state, action, reward, done, and new state. So now we have lists of state, list of action, list of rewards. Each list is the size of batch. And then we convert it to torch tensors. We stack, for example, the states on the first dimension to get a batch of states. Same for the next state. So this should be really simple. Now the agent. Okay, so the agent is where we actually do something with the environment. So our agent will will have an environment. It will have a QNet, which is our network that we're currently using to do the policy, and a replay buffer to save the experiences. Okay, so I'll just show you the main part of the main part here is that in the step of the agent, we take this epsilon, which is the probability to take a random action. So if with probability epsilon, we just take a random action. But with the 1 minus epsilon probability, we take our Q network, okay, and we input the current state, that we're in. The agent remembers the current state, and it gets the cues. What are the cues? The cues are the values of all the actions in that state. So these are the 6 numbers, of course, for each sample in the batch. Okay, and then it just samples by taking the maximum, the argmax here. This is the argmax. Okay, so it's the index of the maximal action, and that's our action. So it uses the Q function, looks at all those 6 numbers, takes the index of the maximal one. Now we have our action, whether it was random or not. We step into the environment with that action, which means we do the action. We get a new observation, next state. Okay, and also we get a reward, and we know whether the episode is done. Okay, so
But this is actually after the system waited like 16 frames to sample forward.
no, you automatically, every time you step, you get, the wrappers do that for you. They do the framing.
Frames and then give you a new.
Yeah, so you got the next state, which is also 4 frames together. Okay, so then you take your replay buffer, you append the current state, the action that you performed, the reward that you got, whether it's done, the episode, and the next state that you got.
Isn't the next state can tell us if it's done or not? Why do you need
Um,
Can I say that the next state is terminal?
how would you represent it? It's still pixels. You'd have to somehow determine from the pixels whether it's done or not. So it's harder. This kind of doing this kind of stuff helps with training, because you don't need to learn the trivial stuff like that. You need to read the game over, or you need to read the score, stuff like that. So instead of reading the score, you get the reward. So it's the same idea. Okay, and we will return. We will not return anything until the episode is done. When the episode is done, we'll return the full reward from this agent. Okay, so a quick sanity check for the agent. Show you that we can do, for example, here 1,000 steps in the agent, and we got some reward, up to 1,000, until the episode is completed. So the agent works. It's able to use our model to sample the actions, and it's storing experiences in the buffer that we gave it. If we look at our agent's buffer and sample 2 experiences from the buffer, we can see the shapes make sense. We have the current state is a tensor of batch size 2, then 4 is the number of frames, and this is the size of the frame. This is the actions, this is the rewards, this is the dones, and this is the next state. So everything makes sense here in terms of the shapes. Okay, now the actual Q-learning part. So we have this, remember, our pointwise loss was defined like that, where we need to create our labels using this formula. So I implemented it as a custom module that does this loss for us. So it will have 2 networks, the QNet, which is the network that we're training, and the target net, which this is generating our target label. And gamma, of course, you need a discount factor. So when you have a batch of states, actions, rewards, dones, and next states, like we got from our experience buffer, first of all, you see what your QNet thinks about them, so you get the action values for that. Okay, but you need to look at only the actions that were performed. Remember, this is the sampling of experiences. So, and here you get the action value for all the actions, but not all actions were performed. The actions that were performed are given to you here in this A. So you need to take the elements from the queues. Okay, so use gather. You take the element from the queues at indexes defined by A. So if A is 2, you will take the second element from the queues, which corresponds to the second action. That's the gather. It just does it in dim1 because of the batches. Okay, it's a bit fast, but basically this will give you the predicted action values for the actions that were performed. Now you need to generate your labels, your Ys. Okay, so you're taking your target network and sampling that in the next states. Okay, because you need the action value of the next state, not the current one, to discount. you get that, and you take the max, because you don't know what action is performed there. You take the max max action. Okay, and if it's done for the dones, then you set it to 0, and then you compute the target label just by the formula. So it's the immediate reward that you got from your experiences, and gamma times the label that you calculated. The Q function from the target network. Okay, so this will be your target. And when you have a target and your prediction, it's just an MSE between them. Okay, so the last thing we need is some training code. Have to keep going quickly. So there's nothing really interesting in the training code. I will leave it to you. I'll just tell you that we're stopping based on the mean of the reward of the last 100 episodes. Of course, we won't really run it for 100 episodes, but this is basically the idea. You look at the mean of the total reward in the last X episodes, and when you see that your mean reward is high enough for you, then you just stop. Okay. So this is the training code. It's not doing anything really interesting. You can just go over it a bit. You can see that it's stepping through the agent. When the reward is not none, it means the experience ended. So it does a bunch of just printing and deciding when to stop and stuff like that. It's not interesting. The only interesting thing is here, where if the episode is not done, okay, so you're not here, the episode is not done, you're in the middle of the episode. So first of all, if your replay buffer is not full, then you don't do anything. You just continue, you keep getting more experiences. You're not doing learning. When your replay buffer is full, then you do learning. But first, every sync target steps, which this is a few thousand steps, you copy your parameters from the Q network to the target network, okay? So you sync them. This is the theta minus. You take the parameters every, let's say, 5,000 steps, copy them to the target network using this save state dict and load state dict. And now, finally, the actual learning is happening here. Note that the learning is happening by sampling from the replay buffer. It does not happen based on the agent. So the agent is just stepping here to fill the replay buffer. And then the actual learning is just sampling a batch of experiences, computing the loss based on our custom module. It takes the experience batches. Okay? And that's it. That's the backward. And you optimize with any optimizer that you want. Okay, so I will kind of just skip this part. I just want to show you the kind of, finally, just to conclude, the result graph from the paper. So this figure shows the performance of this DQN algorithm on multiple Atari games, and it's normalized, so 100% here. Hope you can see. 100% means a professional human. So this is the performance of the algorithm normalized so that 100% means it plays like the best human that exists, while 75% is kind of the average human level. So you can see for example, on Space Invaders, they managed to get 121%. And it's also normalized so 0 is kind of a random playing. It's just a DQN versus a linear learner. Okay, and you can see this last plot here is just showing you the value function. Okay, the colors are the value function of different states. And you can see it learns to give, for example, very high values to the end of kind of the end of a level after all opponents were eliminated, or for starting because both of these, this means that we're gonna get much more enemies in the next step, and this means that we have lots of rewards to reap because there's lots of enemies. So even though they're completely different states, you learn that they are high value. So it means that you're actually learning the value function in a way that makes sense. Okay, so I think we'll skip this and leave you with this nice quote. Thanks.